Hi, my name is Patrick Reagan. Part 4 OSI Model Data Link and Network Layers video will go more in depth of the data link and network layers. It also covers the various technologies that are used in these lower layers. Layer 2, or data link layer, establishes, maintains, and decides how data is transferred from node to node within the same subnet and handles error correction from the physical layer. It also controls how a device accesses to the physical media. Devices that exist on the data link layer are the physical addresses or MAC addresses, Ethernet, Wi-Fi 802.11, bridges, and switches. This layer also ensures error-free transmission over the physical layer under LAN transmissions. Just about any device that makes a physical connection to the network and can move data is on the data link layer. Frames are sent to physical addresses on the same subnet, otherwise known as MAC addresses. If you need to send to a device on another network or subnet, Layer 2 will be responsible to forward the packet to the local router's MAC address so that it can be routed toward its final destination. The unit of measurement used on this layer is frames. The data link layer is divided into the following sublayers, which work together to provide reliable, efficient data transfer across the physical network, enabling communications between devices on the same network segment. Media Access Control, or MAC, deals with the physical addressing, which includes MAC addresses, and access control to the medium. Logical Link Control, or LLC, manages communications with upper layers and provides logical addressing and flow control. The Media Access Control, or MAC sublayer, is responsible for controls how devices on the network access the shared physical medium like the cable or wireless spectrum. It defines the rules for frame synchronization, addressing, and access control. MAC is responsible for adding a MAC address, which is a unique identifier for the network interface, to the data frame, which helps in directing the data to the correct device on the local network. The MAC sublayer also manages contention for the transmission medium, for example, by using protocols like CSMA/CD for Ethernet. Contention refers to a situation where multiple devices on the network attempt to access the same resources, like bandwidth or communication channel, simultaneously, leading to potential conflicts and delays as they compete for access. Logical Link Control, or LLC sublayer, is responsible for managing communications between devices on a network. It provides error checking and flow control, ensuring that data is delivered correctly. LLC also manages multiplexing, allowing multiple network protocols to share the same physical link. It adds headers to the data frame that indicates which upper layer protocols, such as IP, the data is meant for. LLC provides a standard interface for different network layer protocols like IP and IPX to access the data link layer. While it may not be as obvious, the TCP/IP is the de facto protocol suite used today. However, you can have other protocol suites running on the same system, and the LLC will direct the frame to the appropriate protocol suite via the network layer protocol. Media access methods refers to the protocols and techniques used to control how devices on a network can access and share a shared communications medium like a cable to transmit data, preventing collisions, and ensuring efficient communications between devices. Common media access methods include carrier sense multiple access with collision detection, carrier sense multiple access with collision avoidance, and token passing. When a network device wants to access a legacy Ethernet network, the access method used is carrier sense multiple access with collision detection, abbreviated as CSMA/CD. When a computer wants to send data over the network, it will listen to see if there's any traffic on the network. If the network is clear, it will then broadcast on to the network segment. Unfortunately, it is possible for two network devices to listen and try to send data at the same time. As a result, A collision occurs where both data packets are corrupted. When a collision is detected by a sending device, it sends out a jamming signal that lasts long enough for all nodes to recognize it and stop broadcasting. While this is normal for an Ethernet network, both network devices will wait a different random amount of time and try again. Of course, if the network is heavily congested, the network will have more collisions, which results in more traffic, slowing the entire network even more. Today, in Ethernet networks, using bridges and switches create separate collision domains for each port, which avoid collisions from occurring on the Ethernet switch port. Carrier sense multiple access with collision avoidance, abbreviated CSMA/CA, is used in wireless networks. Similar to collision sense multiple access with collision detection, but devices send a signal to indicate their intention to transmit before actually sending data, reducing the chance of collisions. It uses a request to send, clear to send messages is where the device signals its intentions to send data, request to send, and waits for a confirmation from a receiving device indicating it's ready to receive, clear to send, before initiating transmission, essentially preventing data collisions and ensuring smooth data flow. Token passing uses a token that is passed around the network, and only the device holding the token can transmit data. The token is passed from device to device, which indicates when a device can communicate on the network. Think of the token as the talking stick that you can only talk when you have the talking stick. Token passing is considered inactive and obsolete. The data link layer or layer 2 devices forward frames based on destination physical addresses or MAC addresses. They include network bridge and network switch, specifically the layer 2 switch. Ethernet and 802.11 Wi-Fi also operate at layer 2. Layer 3, or network layer, is responsible for the logical addressing and routing of data packets across different networks and determines the best physical path for data to travel from source to the destination. The network layer assigns logical addresses to devices on a network, which are used to identify devices uniquely across different networks. Most common examples are IP addresses, including IP version 4 and IP version 6 addresses. Logical addressing provides an abstract layer of addressing that can be managed independently of the underlying hardware. Logical addresses can be reassigned, reconfigured, and managed through software, allowing for flexibility in network design and management. Logical addressing often follows a hierarchy structure that facilitates efficient routing and network organization. The network layer assigns logical addresses to devices on a network, which are used to identify devices uniquely across different networks. As an administrator, you get to assign the addresses and build a hierarchy as long as you're following certain rules specified by the protocol. The network layer is responsible for forwarding packets based on the destination addresses. Routers, which operate at this layer, use routing tables and algorithms to decide where to send each packet. If a packet is too large for the data link layer to handle, the network layer can fragment into smaller packets. These fragments are then reassembled into the original packet at the destination. Protocols like Internet Controlled Message Protocol, or ICMP, provide error reporting and diagnostic functions, such as those used with the ping and traceroute commands. Circuit switching is a method of data transmission where a dedicated communication path is established between two endpoints for the duration of the communication session. This method is commonly used in traditional voice networks like the Public Switch Telephone Network, or PSTN, but is less common in modern data networks, which is often used packet switching for greater flexibility and efficiency. Circuit switching establishes a specific pathway between the sender and the receiver before any data is transmitted, and the path is reserved for the entire duration of the communication session, providing a constant and reliable transmission channel. This is similar to having an open phone line between two parties. The dedicated path ensures the fixed amount of bandwidth is available for the duration of the communication, which can be advantageous for applications who require consistent data rates, such as voice calls and network resources are reserved for the duration of the session, meaning no other data can use other resources until the session is terminated. Circuit switching involves three phases: setup, data transfer, and teardown. During the setup phase, the network establishes the dedicated path. In the data transfer phase, the actual communications take place. The teardown phase releases the reserved resources once the communications is complete. Circuit switching is primarily associated with the physical layer, layer 1, and the data link layer, layer 2 of the OSI model. However, the establishment, maintenance, and termination of the circuit might involve the upper layer, such as the session layer. There can be an initial delay during the setup phase as the dedicated path is established, but once the path is in place, the data transfer is generally free of delays. Because network resources reserved during periods of inactivity, circuit switching is less efficient for data transmissions compared to packet switching. In early switching, such as associated with the old phone systems, you would have phone operators would have to make manual connections by plugging wires into a board. Today, these connections are done electronically. Packet switching is a method of data transmission where data is broken into smaller, manageable packets before being sent across the network. Each packet is transmitted independently and can take different paths to the destination where they are reassembled into the original message. Packet switching uses data segmentation, whereas data is divided into packets, each typically containing a portion of the data along with a header that includes information such as the source and destination addresses, sequence number, and error checking data. Packets are routed independently based on the most efficient path available at the time of transmission. This can lead to packets arriving out of order, which requires reassembly at the destination. Packet switching is primarily associated with the network layer, which is layer 3 of the OSI model, since this layer is responsible for the delivery of packets across network boundaries, and it handles routing, forwarding, and addressing of data packets between devices on different networks. Packet switching optimizes the use of network resources as packets from multiple transmissions can share the same network links. This reduces latency and improves overall network efficiency. The inclusion of error checking data and packet headers allows for error detection and correction, enhancing the reliability of data transmission. Packet switching is well suited for large and complex networks such as the Internet, as to dynamically adapt to varying traffic loads and network conditions. The network layer, or layer 3 devices, are responsible for routing data packets between different networks based on IP addresses, allowing communications across multiple networks. They include routers and layer 3 switches. Note, firewalls can operate at layer 3 to filter packets based on IP addresses. In the OSI model, layer 1 and layer 2 are considered hardware dependent because they directly interact with the physical network components like cables, connectors, and network interface cards, defining how raw data is transmitted as electrical signals over the medium. While the upper layers deal with logical functions and data manipulation, making them independent of the specific hardware used to transmit the data. Now, layer 2 forwards packets based on the destination MAC address, essentially deciding which port to send the packet to within the local network. Layer 2 devices manage local traffic. Layer 2 devices only look at the MAC address in the packet header to determine where to send the packet. Packets are only forwarded within the same local network segment. Layer 3 forwards packets based on the destination IP address, allowing packets to be routed across different networks by determining the next hop to reach the final destination. Layer 3 devices handle inter-network routing. Layer 2 device will direct the packet to the local device. If a packet needs to go to a remote network, Layer 2 sends it to the local router, and the router will decide the best path to reach the final destination and forward the packet to the next router or hop. While the destination IP address and payload remains unchanged, the Layer 2 and Layer 3 data may change as it navigates the network. As data reaches the router will direct the data to its next hop, which gets the packet closer to its destination. The router will then send the packet to its next hop or router, which will be repeated until it reaches the final destination network. Since the Layer 2 data consists of frames that include the MAC addresses for local communications within a network segment, the MAC address will need to change as data moves between different network segments, and the frames will have to be updated. In other words, every time a packet passes through a router, a new frame is created with updated MAC addresses. Even some Layer 3 information may change as packets are fragmented and reassembled. Packets go through a network address translation or NAT, or the packet's path may change based on the current state of the network and routing protocols. Layer 2 data link layer primarily handles error detection by adding a checksum like cyclic redundancy check to data frames, notifying the sender if errors occurred during transmission on the same local network or physical layer. Layer 2 typically only detects errors and signals to the sender to retransmit the data if necessary, not actively correcting the error itself. Layer 3, network layer, focuses on routing packets across networks and relies on protocols like ICMP, Internet Control Message Protocol, to diagnose and report errors, but doesn't actively correct them. ICMP message reports errors like destination unreachable or time exceeded to the sending device. Layer 3 can adjust routing paths based on error information received through ICMP to find better routes. Layer 4, transport layer, is responsible for full error correction, which means re-requesting data segments if errors are detected, ensuring reliable data delivery across the network. Question: which layer of the OSI model would you find the MAC addresses? Answer: data link. Question: which of the following OSI model layers are responsible for handling packets from the sources to the destination and checking for errors? Choose two answers. Answer: data link and network. Question: which layer of the OSI model would you find logical addresses such as IP addresses? Answer: network. Question: what OSI model layer do routers operate at? Answer: layer 3. Question: what layer of the OSI model does packets operate from? Answer: network. Question: Label the layers that the device operates at. Answer: Layer 3 switch, Layer 3. Cable, Layer 1. Antenna, Layer 1. Switch, Layer 2. Network adapter, Layer 1 and 2. Repeater, Layer 1. Router, Layer 3. For more information, visit these sites. In summary, Layer 2 or data link layer establishes, maintains, and decides how data is transferred from node to node within the same subnet and handles error correction from the physical layer. The data link layer, Layer 2 of the OSI model, is divided into two sublayers: logical link control sublayer and MAC sublayer. Physical addressing uses MAC addresses or physical address to identify source and destination devices on the network. Packet switching is a method of data transmission where data is broken into smaller, manageable packets before being sent across the network. Layer 3, or network layer, is responsible for the logical addressing and routing of data packets across different networks and determines the best physical path for data to travel from source to the destination. Logical addressing provides an abstract layer of addressing that can be managed independently of the underlying hardware. Thank you for watching this video. The next video will be Networking Concepts Part 4, OSI Transport Layer. If you have not already, subscribe to the Pat Has Your Back channel. Thank you.